Signals and systems. Signal classification. Part 1. Problems. Series on signals and systems. Lecture number 1.14. In the present session, our focus is on problems. Problems based on signal classifications, especially the main focus is on periodicity property and even odd nature of the signals. Let us move further to encounter and solve several different problems. To begin with, we consider a problem. It is based on periodic nature of a composite signal. Problem is, find whether the following CT signal is periodic or not. Given signal is x of t is equal to 2 cos 10t plus 1 minus sine 4t minus 1. The signal has two components, one cos, another sine. Each one is periodic, but question is whether the combined signal is periodic or not. Solution. For the sum of two periodic signals to be periodic, the ratio of the periods t1 to t2 must be a rational number. The ratio of two integers. So this is the criteria for the periodicity of sum of two periodic signals. Time period of first part or first component 2 cos 20 plus 1 is 5 by 5 seconds. Time period of second one sine 4t minus 1, it is 5 by 2 seconds. Ratio of the periods t1 to t2 is 2 by 5, a rational number. So the given signal is periodic and its time period is LCM of these two time periods. It turns out to be 5 seconds. We consider another problem. Find whether the following CT signal is periodic or not. Given signal is x of t is 3 cos 4t plus 2 sine pi t. Here the signal has two components, each one is periodic, but it doesn't mean that the combined signal, composite signal is also periodic. Let us see whether x of t is periodic or not. Solution. Time period of first one 3 cos 4t is 5 by 2 seconds. Time period of 2 sine pi t, second signal, it is 2 seconds. Notice t1 is 2 pi by omega 1. Omega 1 is the factor that is multiplying t in the first component. So it is 4. 2 pi by 4 gives you 5 by 2 seconds. In the same way, t2 is 2 seconds. The ratio of the periods t1 to t2 is pi, an irrational number. So the given sum signal is an aperiodic one. Another problem, find whether the following CT signal is periodic or not. X of t is cos t plus sine square root of 2t. So two components are there in the given signal. Again, testing against the criteria, ratio of the periods, rational or irrational, that is the criteria. Right. Solution. Time period of cos t. For this signal, omega is 1. So t1 is 2 pi by omega 1. So 2 pi by 1, it becomes equal to 2 pi seconds. Similarly, Time period of second component sine root 2t. Here it should be root 2. It turns out to be root 2 pi seconds. The ratio of the periods t1 to t2 becomes root 2, an irrational number. So the given sum signal is a periodic one. Another problem, find whether the following CT signal is periodic or not. X of t equal to 2 u of t plus sine 2t. This is the given signal. U of t stands for unit step. Unit step is not a periodic one. Sine 2t is periodic. One is periodic, another is periodic. Just by mere watching, one can have this information regarding the given signal. Now the solution. The given signal is sum of one aperiodic and one periodic signal. Therefore, it cannot be periodic. It is an aperiodic signal. So far, we considered continuous time signals. Now, we move to discrete time domain. Here, we consider a DT signal. Again, the problem is based on periodic nature of the signals. The problem is find whether the following DT signal is periodic or not. Given signal is x of n is equal to cos 2 pi n. One point it requires to be mentioned here. Cos, sine, tan, these functions are always periodic when they are in continuous time domain, but they need not be periodic when they are in discrete time domain. This point has to be kept in mind. Now the solution. For a DT signal to be periodic, the fundamental frequency omega naught must be a rational multiple of 2 pi. The smallest value of positive integer capital N for some integer m in the following expression is the fundamental period. What is that expression? Capital N is equal to m 2 pi by omega naught. The fundamental frequency omega naught of the given signal is 2 pi, which is a rational multiple of 2 pi. So it is periodic. Its fundamental period is n equal to m 2 pi by omega naught equal to m 2 pi by omega naught is 2 pi. The smallest positive value for n is 1. Thus, fundamental period of the signal is 1. Here n equal to m can assume integer. So, smallest positive value for n is 1. Hence, the answer is it is periodic and fundamental period is 1. Another problem, again based on periodicity. Find whether the following DT signal is periodic or not. X of n is 18 cos 20n. Solution. The fundamental frequency of omega naught of the given signal is 20, which is not a rational multiple of 2 pi. So it is an aperiodic signal. Another problem, find whether the following DT signal is periodic or not. The signal, given signal is x of n is equal to e power j 2 pi by 3n plus e power j 3 pi by 4n. So two parts are there, two components are there in the signal. For this we have to determine whether it is periodic or not. Solution. The sum of two periodic sequences is always periodic. By mere observation, one can say that both the individual signals of the above sum are periodic. In case of note, CT signals, two periodic signals together need not be periodic. But in case of DT signals, two periodic sequences together, they are always periodic. This difference has to be kept in mind. The fundamental period of the signal, the first one, it is N1 equal to M 2 pi by omega naught. It turns out to be 3. Similarly, fundamental period of second component, it turns out to be 8. Thus, fundamental time period of the given sequence becomes 24. LCM of these two, N1 and N2, 24. Another problem, find whether the following DT signal is periodic or not. Given signal is x of n is e power j 3 pi by 5 into n plus half. The given signal is x of n. It can be split into two factors. One factor is e power j 3 pi by 5 into half. Another factor is e power j 3 pi by 5 into n. The first part of this expression represents the initial phase of the signal, and it does not influence the wave nature of the sequence in any way, periodic nature of the sequence in any way. Fundamental frequency omega naught of the given signal is 3 pi by 5, which is a rational multiple of 2 pi. So it is periodic. Fundamental period of the signal e power j 3 pi by 5 n is, it can be determined using n equal to m 2 pi by omega naught. So n turns out to be 10 by 3. A few problems on even odd nature of signals. Even odd. Find the even and odd components of the following signal. X of t is equal to cos t plus sin t plus cos t sin t. Solution. Even part of the signal xe of t is half x of t plus x of minus t. So half x of t is the given signal x of t. X of minus t means in place of t, if we substitute minus t, then we get x of minus t, and this is x of minus t. First three terms are x of t, second three terms of x of minus t. After cancellation, we are left with only one term, that is cos t. This is even part. Similarly, odd part can be calculated. Odd part x o of t is half x of t minus x of minus t. So it results ultimately in two components or two parts. One is sin t plus cos t sin t. So even part, odd part. Another problem, this is based on as earlier problem, earlier one, this is also based on even odd nature of the signals. However, earlier one is CT signal, whereas this one is a DT signal. Problem is find even and components of the following DT signal. X of n is given as minus 2, 1, 2, minus 1, 3. Here n assumes minus 2, minus 1, 0, 1, 2. It implies x of minus 2 is minus 2. X of minus 1 is 1. X of 0 is 2. X of 1 is minus 1. X of 2 is 3. Now, the solution. Even part of the signal is half x of n plus x of minus n. Now, we calculate even part using this relation. Consider x e of minus 2, even part. So in this relation, n equal to minus 2. X minus 2 From the sequence, we can say x minus 2, x of minus 2 is minus 2. When we substitute minus 2 here, it becomes x plus 2. X plus 2 is, from this we can see it is 3. So minus 2 plus 3, half. It results 0.5. From this expression, one can see xc of minus n is equal to xc of plus n. Therefore, xc of minus 2 is xc of plus 2. In the same way, xc of minus 1 can be computed. It turns out to be 0. Of course, it is equal to xc of 1. In the same way, xc of 0 also can be calculated. It turns out to be 2. Therefore, xe of n becomes 0.5, 0, 2, 0, 0.5. This is xe of minus 2. This is xe of minus 1. This is xe of 0. This is xe of 1. This is xe of 2. In the same manner, one can compute odd part 2. It turns out to be minus 2.5, 1, 0, minus 1, 2.5 sequence. So these are the problems, some of the problems which are based on periodic nature of the signals, even odd nature of the signals. Here we considered both continuous time as well as discrete time signals in solving the problems. Hope this session is useful to you. We meet again in another session with another topic. So